All right, listen up. Number one, I'm going to do the lesson part first, and then if there's questions on the lab, I'll take them. If you need to turn it in tomorrow, it's fine. Oh, because I know last night was a late night.
Yes.
All right, so the second part of this unit is on periodic trends. And what that means is we're going to look at the periodic table and look at patterns and the properties of the elements. What's most important about this is that you don't just know the trend, but can explain it. Even in the multiple choice, the questions will be something like, which is the larger atom, and then why? In other words, they're going to give you choices that say it's larger because of this, or it's larger because of that. It's smaller because of this, or it's smaller because of that. So just picking isn't enough. You have to understand the underlying theory. That's what I'm going to start on today. What underlying physics principles do you need to understand to make all the arguments? And so that's where we begin now. So we start with the idea, not that idea. We start with the idea of periodic properties of the elements. And it goes something like this. We've already suggested the fact that elements in a group, meaning a vertical column, have similar outer electron configurations. To prove this, let's look at the periodic table for just a moment and look at just the outer part of the configuration. What's the last term in the hydrogen configuration? 1s1. What's the last term in the lithium? 2s1. And sodium, etc. Remember, we called these the valence electrons here? And if you look at every member of the alkali metals and hydrogen as well, they all end in 3s1. If we go to another position, just at random, I'll take oxygen. Oxygen is 1s2, 2s2, 2p4. Sulfur, right below it, is 1s2, 2s2, 2p6, 3s2, 3p4. Again, the valence part is the same for all the elements in this family. And that's critically important because those outer electrons, those valence electrons, are the ones that are most directly responsible for the properties of the elements. So that's kind of the first argument we're making here. Next, let me skip ahead. We want to understand a little bit of physics. Some of you may have seen this before. Many of you may have not, but it doesn't matter. We're not going to do any math with this. It's purely conceptual. Meaning that if you look at what is called Coulomb's law, and you need to know this because this is one of the big arguments you make to justify the periodic trend. Coulomb's law describes the force of attraction or repulsion between electrical charges. So if you look at the equation, F is the force, and we refer to that as an electrostatic force. K is a constant that we don't really need to worry about. The Q1 and the Q2 represent the charges that are interacting. And R is the distance between the centers of those charges. Now for us, they're point charges effectively, so we're just measuring their distance. What you should learn from this is what I've summarized here. What this shows us as a fraction is that if the charges are larger in magnitude, meaning +1 versus +2 versus +3 or -2 minus whatever, the larger the value of the charge, the stronger the force is. That's what this is mathematically telling us. But if the distance is larger, if the ions are farther apart or the particles are farther apart, doesn't the fraction decrease in value when this gets bigger? And therefore the force is weaker. So that's the real takeaway here. If I have two charged particles, the amount of charge and their distance is what controls how much force they exert on one another. And of course you already know that if the charges are opposite, they attract, but if they're the same kind of charge, they repel. You know that. Over here, we're basically making a similar argument, but we've reformulated Coulomb's law in terms of energy, really potential energy, rather than in terms of force. Because sometimes the argument is easier to make in terms of energy. But really, either one of these can make the argument. By the same token, the greater the charge between two particles, the more energy it takes to separate them if they're attracting each other, or to force them together if they're repelling each other. So the more the charge, the harder it is to move them toward or away from each other. And again, the greater the distance, the less energy is between them. With these principles alone, we will largely be able to explain most of how the properties of the elements behave. This is the underlying theory. So I'm going to show you a quick conceptualization of it to make sure it's clear. I'll shrink this down so you can kind of see it as I do it. Close. Can I fit it? I'll fit it here. Okay. So what I have here are two charged particles that I'm allowed to move around. And I just want you to get a sense of this. Right now, just looking at the simulation and the arrows, what do you think the arrows represent? Of what?
Particle.
Well, let's assume they're not moving. It's not their motion, but you're right. They would move along those lines if they were free to move. So what the arrow is a vector representation of something called the force, right?
Yeah.
So watch what happens as I move one particle relative to the other. First, if I move them closer, notice the force is growing. That's consistent because the smaller the distance, the stronger the force. Why are the arrows pointing away from each other? What do you think that means?
They have the same charge, so they're pushing.
And therefore, this is a repulsion. So this might be how two electrons behave when they're near each other. As I bring them closer, they repel each other even more. If they're farther and farther apart, they repel less. And notice that as I move one particle relative to the other, the force direction always follows along the line between the particles. Meaning, you'll notice if you drew a line along the two dots, the arrows always point along that line, right? Now, if I want to show an attractive force, I can start by first turning off one charge and then going the other way, making it negative. You see now the arrows point toward each other? This is indicating attraction. Right now I have two equal and opposite charges. If I move them farther apart, the attraction weakens. Again, consistent with Coulomb's law. But if I take the charges and move them toward each other, the arrows grow, indicating stronger and stronger attraction. If I get too close, it gets really big. Now the other thing I could do to change that force is what? Other than just moving them closer or farther, what's the other parameter I can change?
The charge.
Yeah, so let's leave the negative charge where it is at -1, as if we were talking about one electron. And let's increase the nuclear charge, which would be the positive one, by adding more protons. You see, now it doesn't really physically get bigger. I think they're just doing that to make it clear that the charge itself is more. But you see how the arrow is growing? Because the more charge, the stronger the force.
Well, don't protons have significantly more mass than
Absolutely.
electrons? So the
2,000
nucleus itself would get larger?
That's true. So physically that is true, but this is certainly not even trying to be a scale in any way. But you're absolutely right. The other thing I want to point out is, do you notice that even just increasing one charge affects both arrows? This is essentially Newton's third law, action-reaction, that it's not that one just pulls on the other, they mutually pull on each other. And so even if I just increase one charge, they both feel the difference. They both feel the total force between them. Is that kind of clear now, conceptually for you? Really important you know how charge and distance influences this. Yes? And in terms of energy, we can make similar arguments. As I increase the charge, the energy of attraction, the energy that would take to separate them goes up. It's harder to pull them apart if they're attracting more strongly. Does that make sense? Okay? So, how do we actually put this into play? And is there anything else I have to think about if I'm going to start talking about atomic properties? Well, I'm glad you asked. The concept of shielding. This is the worst possible thing they could have called this. Because it sounds like you're blocking something. I'll give you an example. You're walking in the desert at noon. How does that feel?
Hot.
Hot.
Very hot.
Now, you continue walking, and luckily for you, you come upon a forest. And you walk into the forest. How does it feel now?
Cooler?
Bright. Did the sun stop shining as bright?
No.
So why do you feel cooler? You're shielding, or shielded from the sun a little bit, aren't you? That's what that sounds like it means. But that's not quite right. Because you can't stop the electrical forces of particles interacting with each other. They don't get shielded in the way this is saying. But effectively, they can be shielded, and this is how. Let's say, and I'm going to draw a very kind of loosey-goosey diagram. Let's say you have a positive charge here, and you put an electron out here. We've already demonstrated they feel an attraction between each other. But what happens if another electron hangs out in between? Well, doesn't this and this also attract each other? So that interaction is still there. But don't these electrons push each other away? So as much as this one can push this one away, it takes away from how much overall. No, let me draw that better. That was a bad drawing. So this is still feeling the same attraction as before. But if I'm pushing it away, isn't it effectively like saying overall there's net less inward pull? Like if some of this is still pulling me in like it always did, but some of it is pushing me away, doesn't this kind of feel less overall inward pull? That's what shielding really means. And the reason why it's complicated, as we've already been saying, is we can't even treat the atom like just a bunch of simple particles moving around. We have these clouds and these electron waves and all this junk. So there are ways to kind of get around that and come up with actual values for shielding. I'm going to teach you a rule of thumb way that I think works just fine. Are you ready to learn it? Ready or not, here I come. Back to the periodic table to understand the shielding effect. Number one, let's take hydrogen. Hydrogen has one proton and it has one electron going around it. It feels the full force of that proton at this distance. Again, we're using the fake model of particles to make this easy to understand. So I'm going to define something called Zeph. Zeph. Zeph is Z minus sigma. Huh? Let me define what this really is saying. This is called the effective nuclear charge. Z is the actual nuclear charge. How do I know what the nuclear charge is? It's just the number of protons in the atom. And we know that from the atomic number. S is what we call the shielding electrons. Now, I can show you a little simulation that shows you how to account for each level of electrons and how they influence the others. But you don't need to go that far to make the argument I'm going to make. If I take hydrogen like I just did, okay, it feels the full effect, so we could say its effective nuclear charge is simply 1. It feels the full effect of this proton. If you put a second proton in and start building helium, there's also a second electron in the same energy level. It's 1s2, right? Now, to be fair, they both effectively feel 2 protons, don't they? But is the shielding really 0? Because what do 2 electrons in the same orbital do to each other, based on Coulomb's law?
They push away.
There's some repulsion, isn't there? So there's going to be some repulsion. And in fact, if we tried to measure the effective nuclear charge here, it would be a little bit less than 2 because of that repulsion. Are you following just the general argument? Or? Now, what happens when we go to lithium? It's a little bit more drastic. Because to get to lithium, I add a third proton. But where does the third electron go now?
The next shell.
Yeah, we have to go to a whole new shell. And here's my approximation. This is a rule of thumb, but it basically will give you the right idea. If the electrons are behind me, they are effectively going to shield the protons from me to the degree of 1 for 1. And that's, again, very approximate. It's actually not quite 1 to 1. In other words, for lithium, if I want to ask, well, what's the shielding effect on this outermost electron? Well, it's being repelled by 2 of the electrons. So the shielding effect is 2. But the nuclear charge is 3. So what's the effective nuclear charge on this outermost electron?
1.
3 minus 2. So about 1. In other words, this electron out here is feeling a weaker inward pull because part of its inward pull is being compensated by the outward push of these electrons in between. This is the forest, here's the sun, here I am. Yeah.
So the inner electrons are kind of pushing it outward?
Yes.
Okay.
And ultimately, this calculation is not accurate, but it gives you a sense of what's going on. Because as you're going down the periodic table, aren't you adding layer upon layer of electrons? Yeah.
Why is it 2?
I'm just counting how many electrons are literally between me and the nucleus. And if you make that argument, the reason we have to make at least this much of the argument is because now we have to ask ourselves, how does the effective nuclear charge on these outer electrons feel depending on where we look on the periodic table? There's 2 major directions we have to account for. If we go across one of the periods, what is happening to Zeph? And as we're going down a family, what is happening to Zeph? And if you can understand that, then we can really get in and explain the properties that we measure and why they change in a very regular way around the periodic table. So, consider this. Hydrogen has 1 proton and 1 electron. I'm going to kind of drop like this. Let's drop this. If I go across, I get to helium. 2 protons, 2 electrons. Now, here's my first question. Do you expect the 1s electrons to feel a stronger overall pull or a weaker overall pull compared to the ones in hydrogen? What do you
Weaker.
think? Disagree.
Well, it's 2 protons.
Because they're in the same row, right? So the electrons are in the same level. There's no electrons behind me. So they're just a little repulsion. But it's not going to fully knock out a whole proton's worth of attraction. So I would expect, as I go across, the overall pull for the electrons within the shell increases. Let's prove it by doing the second row a little bit, just so you get a feel for it. Lithium is 1s2, 2s1, but it has 3 protons. Beryllium is 1s2, 2s2, with 4 protons. Boron is 1s2, 2s2, 2p1, with 5 protons. I think that's enough to make the argument. Watch this. Which of the electrons in each case are the core, meaning shielding, and which ones are valence? Which ones are the valence in lithium?
1s2.
The valence first.
2s1.
Oh.
Valence, right? Valence. Valence. But which ones are the core?
1s3.
So the shielding is mostly coming from this layer. Is this layer changing as we go across? So our shielding is staying pretty flat. Again, we'll deal with the consequences of the little side-by-side repulsions later. For now, you need to see the big picture. So as you go across, your shielding is staying about constant, but what do we keep adding into the nucleus?
4 protons.
And that's the bigger effect. So the reason this happens is there's more protons as we go across, so that's more pull, but the shielding is staying pretty constant because we're not adding layers. And because of that, as you go across a row, the outermost electrons are feeling a stronger and stronger pull from one atom to the next. Does that make sense so far? Yeah.
Why would you feel more pull?
Well, every time we add a proton, we're adding more nuclear charge. And according to Coulomb's law, as there's more charge, there's more force of attraction pulling electrons inward. That's the pull they're feeling. Right?
Is that why noble gases don't want to give up anything? Because they never want to give up any of their electrons? 'Cause
It's
they're
getting
super
to that point because what we would notice is at the end of the row, the outer electron shell is the most strongly held. So it would be much harder to remove that, absolutely. You're right. There was a question? Bill?
Well, just like the 1s2, that's the core because the first shell that can take up 2 electrons, right?
Yeah, and you can't fill it anymore. So the core is simply all the electrons behind the valence. So really, if you think about it, the core electrons are the ones between me and the nucleus, if I'm in the valence shell. Okay? Yeah.
How come our periodic table doesn't have the extra elements at the bottom?
Well, they just shoved them in here instead of dropping them down. It's
No,
the
I
same.
mean, for these ones. Like,
Oh, this is an outdated one. This,
Oh.
because it's digital, it's updated regularly. And right now, current knowledge puts us to 118 that we actually have characterized and identified. Even though they're synthetic, they have enough information or data to justify saying, yeah, we found it. They make a few atoms at a time. They look for the decay signature and go, this is it. They don't even have it like in a vial somewhere. They literally make a few atoms and go, we got it. All right, now, that's the story going across. Going down the periodic table, let's start at lithium and go to sodium. Sodium is 1s2, 2s2, 2p6, 3s1. Oh my gosh, it has 11 protons. So much more pull, right? But watch this. You see all of these electrons here? Aren't these all acting as shielders? And there's just this one little valence guy out here. Now let's do my simple math. 2, 4, and 6 is 10 shielding. Subtract that from 11. And technically, you really only are looking at about +1 effective nuclear charge on this. So the effective nuclear charge, if you go down a family, is staying pretty flat because you keep subtracting all the intervening layers as shielding electrons. So the effective nuclear charge is staying pretty flat. So that's not really the story going down. Then what is? Why aren't all the atoms the same when we go down the family? Something else is going on that's affecting the force that they feel. What's the other factor?
It's the inner shells, the number of inner shells, the number of core.
More shells, which means the outer electrons are where relative to the nucleus? Farther away. And when you're farther away, what does that mean? In terms of the force you feel?
Less attraction.
Yes. So, to summarize what we're saying, the main story as we go across the periodic table is that the increased in effective nuclear charge means that there's a stronger attraction for the outer electrons from the nucleus. Outer, again, meaning valence. And that's really the key takeaway. But when you go down the periodic table, the layering of all the different shells is keeping the attraction approximately, well, not the attraction, but is keeping the effective nuclear charge approximately constant. So going down, it's more about the layers. Almost every argument you're going to make, to simplify it, is going to come down to this. Going across, it's the more protons argument, because that's the bigger factor. Going down, it's the more shells argument. Weaker force. If you can hold on to that, and just remember Coulomb's law is behind it, you've got everything you need to make the arguments. How you feel about that so far? Jess? No? Maybe so? So now let's try to predict. Without me even telling you the answer, I want to see if you come up with the right idea. Can I erase what I scribbled just so? Let me just do this too. I'm gonna mute the, just so it gets a nice image on the camera too for people at home. If you're looking at this from home later, just pause it at this point to write this down. Thank you. What? Oh, no. Oh, nobody really, but there's some people missing that I'm filming this. Again, I keep saying film, it's hilarious, but there isn't. All right, now, here's my first question. When I ask you how big an atom is, what do I mean? Like, how do you even measure the size of an atom? Any thought? The weight is one way, but it's not what I'm asking. I'm asking the physical size. Like if I asked you how big a basketball is, how might you explain to me the size of a basketball?
The diameter.
Diameter or radius? And we all understand that if you had a basketball, well actually this would be kind of tricky, wouldn't it? How would you get to the center or get across it to measure? I guess you could wrap a string around it and find the circumference and calculate it. But you can't do that with an atom, right? You want to see a cool thing you can do with an atom though? If you get a regular crystal and you treat the atoms as if they're solid spheres, which you can approximate, what happens is their nuclei are fixed distances apart. And when that's true, there's ways through X-ray crystallography, diffraction really, where you can get an image that measures the internuclear spacing. So if I can do that, isn't this distance basically twice the radius of the atom? If we have two atoms next to each other and their nuclei, we know that separation. That's one way we can actually measure an atomic radius. Kind of crazy when you think about measuring something so small. But atomic radius is one of the trends you have to understand. And it just measures the size of an atom. And there's different methods of doing this. There's this technique. There's other theoretical ways to do it. Long story short, atomic radius is the size of the atom, if you think of it like a sphere. Here's my question. If I picked any row, let's take the second period, the second row, and I asked you, what do you think the size of the atoms does as you go left to right? Do they get bigger or do they get smaller? That's the question. What do you think, based on what we've said so far?
Bigger, I guess.
Bigger. Interesting. More?
I think smaller.
Smaller. Interesting.
Because
Justify bigger first. If you think bigger, justify it. Why do you think they get bigger? And it's okay. I'm not saying who's right or wrong right now. I'm asking you to justify your answer so we can analyze what you're thinking.
Just off like common knowledge, so like the atomic mass or the electrons.
Well, here's the thing. I didn't ask if they're heavier, right? See this piece of paper? I'm going to crumble it. Okay? It weighs a certain amount right now. Do you agree? How big does it look here? So, you see the size? Now, what's happening to how strongly the electrons are being attracted as we go across?
It's going higher.
It's getting stronger. So how would I simulate this with this paper?
Push it inwards.
Wouldn't it be like it's getting pulled in more and more and more? Is this getting bigger to you?
No.
Why not? Because it's being compressed.
Not bad.
It's okay. Do you understand now? If you connect the fact that the electrons are not solid objects, but these kind of wave-like clouds that we've been describing, that thing can be compressed to an extent. And so as the number of protons in the row increases, it's pulling the electron shells closer in. And for that reason, the atomic radius is actually decreasing in size as you go across. Now there's a limit to this, of course, right? You can't compress it ad infinitum. It's going to reach a limit. In fact, if you look at the graph of this, it's actually really cool. Check this out. This is data that I plotted on a graph to show you how the radius of the atoms is changing as you go across the periodic table. So, they're in order of atomic number. This is hydrogen, and this is helium. That's one step across. Look at the shrinkage. Then we go to lithium, and as soon as you go to the very next element, beryllium, look at that huge drop in radius. Right now I've plotted here the radius, here's atomic number.
Why is it so drastic?
Because the first addition of the proton causes quite a shrinkage, but what happens is as the electrons start getting closer and closer packed, kind of like me packing the paper, it reaches quite a limit because now I'm getting the electrons too close, and the repulsions, and really the Pauli exclusion principle ultimately, is preventing them from getting much closer. So that's why you see that drop off. But look at how consistent this is. As you go across the row, you reach a bottom, guess where? At neon, the smallest one in its row. And then you start a new row, and you see it. You can literally see from the properties a periodic table here. Here's the first row, here's the second row, here's the third row, here's the fourth row, and then here come the d electrons. It literally comes out visually from graphing the property. Now, the graph already answers my next question, but let's see what your argument would be. What do you expect the atomic radius to do as you're going down?
Bigger, it gets bigger.
Yeah, it gets bigger.
Because it's,
That one I hear more confidence.
that's less attractive.
Okay, is it just the attraction, or what's the more important
More
factor?
electrons. More
Number of shells.
More shells. If you ever made a snowman, you know what I mean.
Yeah, more shells.
So to do the analogy, if I take this and I wrap another one around it, isn't it going to be bigger even if I try to squish it? And if I do it again, God, I hope he doesn't need these. You see, I keep adding layers, and it keeps getting bigger even though I'm still squishing it. That's the key. Now check it out. You can see that right off the graph that I just showed you. Let's look at the top member of each family, or the first member, not the top. Here's hydrogen. This is element number 3, lithium. Much bigger. After lithium, what's the beginning of the third row? I believe it's sodium. You see the tallest of peaks are the beginning of each row. And the smallest atom in each row are the noble gases, right at the end of each row. Does this make sense? What do you think?
I think that'd be a little more aggressive.
That's fine. So, let's practice. I'm going to go to the periodic table now. I'm going to put just a generic periodic table like you see it. I'm going to pick 2 elements, and you tell me which one's the bigger size and why. Okay? Oh, go ahead.
Can you go back to the chart for a touch?
The graph?
Yeah. Because, like, if you're to ask, like, which radius is bigger, like, beryllium and, like, argon, how would we know?
I see. So some of the questions would be kind of unfair and hard to, like you're saying. And let me show you what I mean by that. So if I ask you this, if I said which is bigger, magnesium or phosphorus, which would be the larger radius atom?
Magnesium.
So we would pick this as larger. And then what argument would we use to explain it? Using Coulomb's law / shielding / whatever principles we just talked about.
Has less protons, so less.
Less attraction.
Fewer protons, less attraction is fine. And I think it's important to convey the fact that since they're in the same row, we're talking about the same shell, right? If you don't say that, it's not enough to me. Like, you have to explain fewer protons, but same valence shell or something like that. So that we understand that the real factor that's changing is just the protons primarily. Now, your question was, well, how would I say take this one and maybe compare it to something like that one? Because now we have opposing forces. Going across should shrink it, but going down should grow it. I think to some extent it's an unfair question, because how are we supposed to scale which factor is more important? I can give you somewhat of an answer, but I just don't think you'd be forced to answer them that just
So they
drastically.
wouldn't ask a question like that.
You might get them to a degree, but not drastic, and I'll show you what I mean. Because if you looked at the graph that I showed you, you saw how the shrinkage dropped off.
Yeah.
So as you go to the right side of the table, the shrinkage is kind of maxed out, and now adding the layers is really a much more important factor. So at the beginning, you saw a drastic drop. So the question is 1 over more than 1 down? And I think that's something that's debatable. I wouldn't expect to be asked that, because it's not fair. It's kind of confusing. Having said that, now if I asked you which one is bigger, sodium versus cesium, which is the larger one here?
Cesium.
And the argument to make this larger is simply what? More shells, and that's enough. Yeah.
So on the right side, it would be like Iodine would be larger than silicon because as you move farther to the right, it has less effect.
Agreed. Agreed. So based on what we saw on the graph, going 3 across at this point is hardly shrinking it anymore, but now we're adding 2 more shells. Now let's see if that argument holds water, because we still might be wrong. I could be off. So the nice thing about this is when you click on the Properties tab, like I have, instead of the Electrons tab, you can actually see the properties. Let's see, which one do I want? Am I in the right spot? Let's see. Yeah, properties. So now I can pick a particular, it used to let me, see if it still does. Looking for radius. And I'll just go with calculated radius. No, we'll go covalent radius. Oh, they changed it. They used to make it so you could see like the color scheme on this table, unless I'm on the wrong spot. Thought. Oh, there it is. Oh, right there. You see how it's color coded? Right now, the darker the color, the bigger the atom. The lighter the color, the smaller the atom. So you can see where the largest atom is. Bottom left.
Bottom left, yeah.
Weakest pull, most shells. Where are the smallest atoms?
Top right.
Strongest pull, fewest shells. And you just asked about silicon versus, what was it?
Iodine.
Silicon has a size of about 111. Iodine's about 100, I think it's 33.
35.
It's a 3. This is 133. So does your argument hold water? Absolutely. Let's look over here. Let's compare sodium versus calcium. We went across one, which should shrink it. We went downward, which would grow. On this side, 1 over has a huge shrinkage at the beginning. So if you look here, this one's 154, and this is, I think, in picometers. Right? Double check. Yeah, picometers is what, 10 to the minus 12th meters? So we're talking about small things here, folks. This one's 174. So even here where there's a drastic shrinkage across, adding the shell still made it bigger. Now we have to be careful. Covalent radius is one thing, there's other ways to measure the radius, and sometimes the numbers disagree. I don't care about all that detail. Can you make the basic argument? That's the main thing you have to understand. Now we spent a lot of time on radius today because if you understand the radius argument, we're going to apply it to all the other trends tomorrow. I know I put homework up, however, don't think of the homework right now as due tomorrow, because I don't know that I've given you enough. You can start it and maybe do a few of the questions. Whoops, I'm on the wrong tab here. So 1, 4 through, basically problem set 4, you're going to do all 16 questions over the course of the next couple days, okay? You can think of it as due on Monday for all of it, and I'll probably wait till Monday to quiz it. Okay? We'll finish this lesson mostly tomorrow, and we'll review it on Monday, and then we'll practice. The test is on Wednesday next week. If you have the lab ready, you can turn it in. If you still want to finish it, you can give it to me tomorrow. It's fine. Okay? That would be your only homework then.